Howdy, my name is Broussard. I'm joined with my colleagues Brian Arnold, Bailey Brawley, Carter Gehm, Samuel Helgren, and Justin Wallace. We are all seniors in the Mechanical Engineering Department, and our project is COOP, or Carbon Dioxide Purging, sponsored by industry partner BP. Before we can discuss our project, we have to cover a little background of what purging is. Purging in the context of the oil and gas industry is a process used to remove flammable fluids from a vessel. This is done prior to maintenance where an open flame would be used, such as welding. This short animation shows the purge medium from storage to exhaust, and the industry standard medium is nitrogen since it is inert and highly available in the atmosphere. First, a storage vessel is filled with cryogenic liquid purging medium and maintained at low temperature, high pressure. When purging is required, the liquid is pumped through an ambient air heat exchanger, or vaporizer, to phase change the fluid into a vapor. It is then regulated down to a safe but still high pressure. Here we have the purge target vessel, shown red to highlight its flammability. This vessel is initially at atmospheric pressure, but the purging medium is pumped into the vessel until a desired pressure is reached. This mixture is then exhausted to the flare, back to atmospheric pressure, and the remaining gas mixture is now less explosive than the initial mixture. This is done multiple times until the mixture no longer contains a flammable environment.
The initial objective of the project was to find a feasible alternative purging medium to nitrogen for use in the purging process. Through extensive research and calculations, carbon dioxide was determined to be the most viable alternative. In order to deliver the most useful product to our sponsor as possible, the project expanded in scope to create what we call the feasibility calculator. The feasibility calculator is an Excel-based computer program that accepts case-by-case user inputs to simultaneously compare two different individual purging scenarios. The comparison can be as simple as a difference in only the purging medium used, and can be as complex as comparing entirely different purging procedures or vessels. The input cases are analyzed and compared with respect to economic, environmental, physical, and safety considerations.
The methodology for completing this feasibility calculator was to break it down into individual subsections. After those subsections had been completed, they were linked together and with the user interface to allow for seamless user inputs. Looking at the different subsections, the physical portion uses custom interpolators to find the thermodynamic properties at each state. Individual purge passes were analytically completed with in-depth calculations based around the ideal gas equation. The major outputs using these calculations was the gas mixture composition in the purging atmosphere after each purge. As far as the safety portion, our calculator can perform ISO flammability calculations to determine if the purging atmosphere is safe and to determine the purging effectiveness. The economic portion calculates the total cost to purge, accounting for lost revenue, shipping, monthly purging requirements, and purchasing costs. All of the outputs are customizable depending on which parameters the user wants to include, and the lost revenue calculations were based on inputted reg specifications and Mueller calculations to find total purging time. The environmental portion calculates the energy required to separate the purging medium from the source, compress it to the storage pressure, and cool it to the storage temperature. The equivalent US carbon output is used along with the purging vessel volume to calculate a total equivalent carbon output to the environment in units of pound mass of carbon dioxide.
In order to improve the functionality of our feasibility calculator, we created a user interface area. This is where all customer interaction takes place, such as entering inputs, selecting calculation types, and receiving outputs. A partial section of this interface is pictured on the slide. There are many drop-down menus that allow the user to interact with different options in the tool. This allows the user to perform broad calculations or perform more of an in-depth analysis where detailed information is required, such as pre-purge atmosphere composition. In addition, acceptable ranges are listed next to the inputs to guide the user, and error checks will occur if the user enters invalid information. So in order to verify our feasibility calculator outputs, we utilized two chemical process simulators. The team dedicated time to learn Aspen HYSYS and DW Sim, and we created several purging models that were then compared to our feasibility calculator. In the end, we were able to validate our project by finding negligible error between the simulations and our feasibility calculator.
So what is the benefit of our project? The largest benefit is our calculator is able to determine the optimal purging gas on a case-by-case basis with respect to the economic, environmental, physical, and safety factors. An economic example would be, does one gas cost less to purchase at a certain volume range, or on an offshore oil platform where the goal is to always reduce downtime cost? Could purging with either gas reduce this time? Environmentally, what is the difference in CO2 emissions with using each gas? For the physical side, what storage conditions are required for each gas, and what would the required heat input be to vaporize it? Our calculator can't answer all of these questions. The next benefit is designing new purging systems. Say you wanted to retrofit a current nitrogen purging system to be used with CO2. Our calculator can find the thermal capacity needed for the new vaporizer. The final benefit is improving purging practices and finding deficiencies in current systems. An example of this is, if it is possible to increase purge pressure, could that reduce our required purge passes and therefore reducing downtime? We would like to give a special thanks to our project sponsors at BP, Colin Claypass and Joe Cunningham, as well as our professor, Dr. James Hubbard, our teaching assistants, Lisa Devesh, and everyone else that assisted in the development of the project over the course of this past year. Thank you for watching our engineering project showcase presentation.